Assalamualaikum and salam sejahtera to all students. So I will continue with our lecture sessions. Okay. So last week we have learned about amplitude modulations. We have stopped up to this topic, which is the vestigial sideband VSB. Okay. So if you still remember that amplitude modulations has a few types. Okay, the first one is the double sideband full carrier DSB-SC. Second one is the double sideband suppressed carrier DSB-SC. And remember that in double sideband suppressed carrier, we suppress the carrier component completely. Okay? And it still has two sidebands, lower sideband and also the upper sideband, but it does not have the carrier component. Okay, and then another type of AM amplitude modulation technique is the double sideband reduced carrier. That means we reduce the carrier component up to certain percentage. And then we have single sideband amplitude modulation. Okay, single sideband with carrier or single sideband without carrier. So in the single sideband, we have only one sideband, and either we have the carrier component or not. Okay, single sideband, that means we can choose either the lower sideband or the upper sideband. Okay, and then the last one is the vestigial sideband VSB. Okay, so in the vestigial sideband, we still have double sideband, the lower sideband and also the upper sideband, and also we have the carrier component. Okay, but this time you're gonna see later that the lower sideband and the upper sideband are not equal. Okay, so this VSB is used in the TV broadcasting. Okay, which means that the signal can carry both audio and video signals together in one signal. So the TV signals consist of picture, video signal, and also the audio signal. So audio carrier is a frequency modulated, while picture carrier is amplitude modulated. Okay, so uh, the signal will carry both of these. Okay, the audio and also the video. Okay, so video information typically contains frequency as high as 4.2 megahertz up to 8.4 megahertz, a fully double sideband. Okay, so this um, shows that the video signal needs higher bandwidth compared to the audio signal. Okay, so remember that video will consume a lot of bandwidth compared to the audio signal. Okay, so um, uh, excessive amount of bandwidth will be used. Okay, so these VSB is used in order to avoid a wasteful of bandwidth. Okay, because if we use a double sideband full carrier, it's gonna wasteful of bandwidth. Okay, because not all of it is required to reliably transmit a TV signal. Okay, so therefore, in order to avoid a wasteful of bandwidth, okay, untuk mengelakkan berlakunya pembaziran bandwidth, so therefore it come up with the VSB. Okay, the VSB is to help in order to reduce the amount of bandwidth consumed to transmit both audio and video signals together. Okay, so we use this kind of modulation system to avoid wasteful, okay, to avoid wasteful in the bandwidth regions. Okay, so how does VSB able to reduce the excessive amount of bandwidth used to transmit both video and audio signals? Okay, so there are way that there is a method for the double sideband vestigial sideband to transmit both the audio and video signals. So let's look at this slide. Okay. Uh, so over here, okay, F, this is for the vestigial sideband. Okay. So if you see from here that uh, first of all, the amount of power carried by the lower sideband and the upper sideband is not equal. Okay, if we remember in the double sideband full carrier, the power in the lower sideband and also the power in the upper sideband are equal. But now in the vestigial sideband, both sidebands produce or consume different values of powers. Okay, so the upper sideband in this case, if you see from here, PUSB uh, carries video signal, whereas for the lower sideband, PLSB carries for the audio signal. So first, you see that the power for the lower sideband is less than the power of the upper sideband. Okay, and then in terms of the size of the bandwidth, okay, the width of this band, upper band, is larger than the width of the lower band. Okay, so that's why the upper sideband here is more suitable for the video, and this one for the lower sideband is more suitable for the audio signals. Okay, and we also still have the carrier component. Okay, we still have the carrier component. So if you see from the picture above, picture E, so this is for the independent sideband. Picture D, this is for the reduced carrier single sideband. So this is for the single sideband modulation scheme where we have only single sideband and reduced carrier component. Okay, so the carrier component has been reduced very much. Okay, a lot of carrier component has been reduced. And if we go to picture C, okay, so this is for the for the single sideband suppressed carrier. Okay, this means no carrier component. Okay, the carrier component is 0. And then picture B is for the full carrier single sideband. So this is for the single sideband with carrier. Okay, we have the upper sideband, we have the carrier component, and we don't have the lower sideband component. Okay, and then picture A is for the conventional AM, which is a double sideband full carrier. So we have the upper sideband, we have the lower sideband, and also we have the carrier component. So if you see from here, the amount of power for the upper and lower is the same, and the size, the bandwidth, both upper and lower also the same. Okay, so double sideband full carrier, if you see from here, the upper and lower sideband are duplicate to each other. Okay, whereas for the vestigial sideband, it is different because it carries both audio and video signals. Okay, so if we have the same amount of bandwidth for the lower and upper sideband, we're gonna waste a lot of power. We're gonna waste a lot of bandwidth. Okay, so in order to avoid the to avoid wasting a lot of bandwidth because of the video signal, we can use the vestigial sideband. Okay, so advantage of the vestigial sideband compared to the single sideband. So in terms of design of the sideband filter is more simplified. No need sharp cut for the filter, and it also improve low frequency response in the vestigial sideband compared to the single sideband. Okay, so which one to choose? Which modulation scheme that we need to choose for our application, for our system? Okay, it depends. Okay, so each type of amplitude modulation has its own advantage, and also it has some disadvantages depending on the application type. Okay, so when we want to choose the type of AM modulation scheme, we can see based on, we can choose based on a few factors. Okay, the first one is the we can see from the perspective of the bandwidth allocations. Okay, so if the application needs smaller bandwidth, that means we need to choose single sideband. We cannot choose double sideband full carrier. Okay, and again, power. Okay, some system require a low amount of power. Some system does not matter. Okay, doesn't matter. So it depends. Okay, so if the system requirement needs to have to produce a low power, that means we need to choose single sideband. Otherwise, we can choose double sideband. Okay, and then signal to noise ratio. Okay, SNR. So again, for the signal to noise ratio, single sideband is more single sideband will produce a better signal SNR compared to the double sideband. Okay, and remember that in terms of noise power, okay, PN is equal to KTB. Okay, so the higher the bandwidth, the higher would be the noise power. Okay, so if the noise power becomes higher, that means the SNR becomes lower. Okay, SNR is equal to S signal power over noise power. Okay, so we need to choose a modulation scheme that produce the least amount of noise so that we can achieve higher SNR. Okay, that means if you want to have a better SNR, we can go towards a single sideband modulation scheme. Okay, and then we can also see in terms of you can also choose based on the complexity, circuit complexity. Okay, the more complex is for the single sideband. The single sideband is more complex circuit. But if you want to choose a simple circuitry of the system, we can use a double sideband full carrier. So double sideband full carrier is less complex for the circuitry design. Okay, and then we can also choose based on the cost. Okay, the least amount of course, for the double sideband full carrier. Okay, because the circuit is more simple. The circuitry is more simple. Okay, the more complex the circuitry, the higher will be the cost. Okay? And then in terms of distance, okay, in terms of distance. So distance, if the transmission, if the distance between transmitter and the receiver are farther away, we need to choose modulation scheme that can produce higher amount of power. Okay, higher amount of power. But here we need to see again that the amount of power that we need is actually in the sidebands. Okay, so we need to choose the modulation schemes that produce the highest amount of power for the sideband, which carry the information signal. Okay, so this one is subjective. Either you want to choose a single sideband. Of course, in the single sideband, you're going to see that the amount of power in the sideband is higher compared to the amount of power in the sideband for the double sideband full carrier. Okay, so we have seen about the type of AM. Okay, so now we need to look into the next topic on how we can produce the amplitude modulation signal. Okay, so the AM signal is produced by the modulator, uh, by the um, by the modulator block circuits in the transmitter. Okay, so inside the modulator, there are a few processes happens. Okay, so we're gonna see that we're gonna see later how this AM signal is produced. So okay, so if you see from here, amplitude modulation voltage is produced by a circuit, then can multiply the carrier by the modulating signal and add the carrier. So we're going to see this later. Product of the carrier and modulating signal can be generated by applying both signal to a non-linear component such as diode. Okay. Intermodulation products, third, fourth, and high order harmonics are produced by the diodes and transistors, and tune circuit to filter out the modulating signal and carrier harmonics, leaving only the carrier sideband. So we're going to see these processes happens in the modulator circuit. Okay, so this is the simple AM circuit block diagram where we have the multiplier here, which multiply both carrier and also the modulating signal, and also we have the adder over here, okay, to sum up the components of the carrier and also the multiplications component. Okay, so we're going to produce a VAM here, which is we have three component. We have the multiplication component and also the summation component. Okay, remember from the envelope equations, VAM. Okay, so we have the uh, VC plus, okay, VC plus VMT multiplied with sine 2 pi FCT. Okay, so we have the uh, addition component and also we have the summation component. Okay, so there are two types of amplitude modulators. There are low level and also high level modulator. Okay, so modulators, AM modulator can be divided into two, which are low level modulator and also high level modulator. So low level modulator generate a small amount of power. Okay, and then the modulator produce a small amount of power, and this signal needs to be amplified before transmission. Okay, and for the high level modulator, the modulator produce an output signal with high power, and this signal is suitable for transmission, for direct transmission, so you don't need to put additional amplifier before transmission. Okay, so the keyword here is that low level means low power, high level means high power. Okay, so for the first type of AM modulator, okay, so we have number one here is a diode modulator with tuned circuit filter. So this is the simplest circuit for the modulator, for the AM modulator. Okay, so if you see from here, we have two signal generator for the modulating signal, the input message, and also for the high frequency carrier. Okay, we have the resistor over here, R1 and R2, and also R3 over here. And we also have diode over here. Okay, so remember what is the function of diode? The function of diode is to allow current to flow in one direction only. Okay, that means there's no reverse bias. In this case, current will flow from here to here, from positive to negative side, and there's no reverse bias. Okay, there's no reverse bias. And then here we have LC tank circuit. Okay, LC tank circuit, which resonate at the carrier frequency. Okay, so this LC tank circuit is also uh, uh, like this LC tank circuit will also be like a, okay, so this LC tank circuit will resonate at carrier frequency, and it also do the function like a battery. Okay, fast charging battery. Why it is like a battery, we are gonna explain later. Okay, so this LC it will resonate at the carrier frequency. And another thing is that it will do the function like a fast charging battery. Okay, so this diode modulator has come out in the previous test and exams questions. Okay, so the students were asked to explain about the process happen inside the diode modulator. Okay, so what happened in the diode modulator? Okay, so we're gonna see from here. So this is the modulating signal, the information signal, and then here we're gonna have the carrier signal. So the carrier signal has a higher frequency compared to the modulating signal, the input signal. Okay, so you're gonna see that the ripple is very close to one another because this is a higher frequency compared to here. The ripple is not close to one another because this is a lower frequency. So here this is a lower frequency and carrier has a higher frequency. Okay, and then if you see from here at this point, okay, so this is the point where both signal are mixed together. Okay, modulating signal and also the carrier signal are mixed together. So how does the mixing process happens? So when the mixing process happens, okay, both carrier and modulating signal will mix together. And if you see from here, okay, the output of the mixing process, okay, the output of the mixing process uh, like this, okay, it has the carrier frequency, but it follows the shape of the modulating signal. So this is what happened after mixing, okay, just mixing together. Okay, and then the signal goes through the diode. What happens? Okay, you see that here go to the diode. So remember that diode only allows current to flow in one direction only. Okay, so that means diode is also like a switch, okay, on and off switch. So what happened? You see that from this signal, okay, we initially we have the positive cycle and also the negative cycle. Okay, so if you see from here, the signal supposed to be down, like go to the negative side like this. Okay, however, the diode prevents the reverse bias. So that's why when the signal moves from positive to negative, it will be cut off. Okay, the negative side will be cut off. So all of the negative sides here will be cut off. Okay, so it's supposed to have negative sides like this. Okay, however, due to the diode, uh, the negative side has been cut off, clip off. Okay, due to the diode. Okay, so this is the output of the diode. Okay, which we see that the negative cycle has been clipped off. Okay, so we see only the positive cycle of the signal. Okay, and remember that uh, what happened during the positive cycle of the output signal is that the LC tank circuit will be charging. Okay, so during the positive cycle of the signal, okay, like this, okay, the LC tank circuit will be charging. And during the reverse bias, what happened is that the diode will be open circuit, switch off, and this LC tank circuit will discharge. Okay, this LC tank circuit will discharge during the negative cycle of the signal or during the reverse bias. Okay, So the LC tank circuit actually will complement the output signal. Okay, what I mean complement is that during the reverse bias or during the negative cycle of the signal, which has been clipped off, it actually will discharge. The LC tank circuit will discharge, and you see that this at the negative side here, this is produced by the LC tank circuit. So you see that from here, the LC tank circuit will charging, okay, and then during the negative cycle, is actually the reverse bias. The diode will clip off the negative cycle, and at this moment, the LC tank circuit will discharge, and then LC tank circuit will charging. Okay, the output here, LC tank circuit charging, and then at the negative side, the diode will clip off the negative side. Over here, you're gonna see that the LC tank circuit will discharge. Okay, so when LC tank circuit discharge, it will complement, okay, the output signal. So that's why we're gonna see a full envelope like this. Okay, so here LC tank circuit will charging and then discharge, which will complement the signal, the output signal, and then LC tank circuit charging again, and then LC tank circuit discharge to complement the output signal, charging, discharge, charging, discharge. So this process will produce a complete okay, output waveform, a complete double sideband full carrier signal at the output. Okay, so LC tank circuit resonates at carrier frequency, which will cause oscillation, okay, creating a negative half cycle for every positive cycle. Okay, so it creates a negative cycle only at the frequency of the carrier. Okay, so resonates means that it will operates. Okay, it will operate at the carrier frequency. So that's why during the negative cycle it will oscillate, which produce the negative cycle of the output. So that's why at the end of the circuit, we're going to see a complete double sideband full carrier waveform. Okay, so for all students, these processes have been asked during the previous semester's exam and also in the test, where students needs to explain what happened in the circuit. The process happens in the circuit at this point after the diode, and at this point at the end, which is the students needs to explain based on this explanation and also draw a simple diagram, a simple waveform like this. Okay, and then the second type of modulator. Okay, the second type of modulator is transistor modulator. So instead of using diode, we can also use transistor. Okay, remember transistor, the function of transistor works also like a diode. Okay, but transistor only allows current to flow in one direction, which is to, to function as a the function of transistor is like a diode also, okay, which allow current to flow in one directions, which is like a switch. Okay, and transistor also function as a amplifier. Okay, so there are two basic function of transistor in the system. Okay, and also as the amplifier. Okay, so transistor modulation consists of resistive mixing of network, a transistor, and LC tune circuit. So we still have the LC tune circuit. So the emitter-based junction of the transistor serves as a diode and also a non-linear device. Modulation and amplification occurs as the base current controls larger collector current. So remember in transistor, the base current control the output, okay, control the amplitude of the output. Okay, so the LC tune circuit oscillates to generate the missing half cycle. Okay, so during the negative cycle is clipped off by the transistor, and the LC tune circuit will oscillate and generate the other missing half cycle. Okay, so here you see that we have two signal generators for the carrier and also for the information signal, modulating signal, connected to the base of the transistor. Okay, so and here you see that the collector is connected to the LC tank circuit. Okay, we have the L and also C tank circuit connected to the VCC. Okay, so when the current, okay, when the current in the base, okay, when the current at the base more than the threshold limit, okay, then uh, the transistor will be a closed circuit. That means the current, okay, so okay, so when the current at the base more than the threshold, more than the transistor threshold, okay, base threshold, that means uh, the transistor will function as a closed circuit, so the current can flow. Okay, the current can flow from collector to the emitter. Okay, however, when the current at the base lower than the threshold limit, so this transistor will uh, will be open circuit and current cannot flow from collector to the emitter. Okay, so this is what happened when the current at the base lower than the threshold. Okay, so remember, transistor has a threshold limit. Okay, if the current at the base I base is more than the threshold, so that means current can flow and switch on. Okay, when the current at the base lower than the threshold limit, that means the transistor will switch off, so current cannot flow from collector to the emitter. Okay, so what happened from this process, you're going to see that so when both carrier and modulating signal are mixing together, okay, during the mixing process, of course, it will looks like this, mixing process. Okay, so when the current more than the when the current at the base is more than the threshold limit, okay, so it will switch on. Okay, and when the current is below the threshold limit, it will the transistor will switch off. So what happened is that uh, when the current goes sorry, when the signal goes to the negative from positive to the negative cycle, so the transistor will clip off the negative peak cycle. It will clip off the negative cycle of the signal. Okay, so this is actually the output. Okay, when this is actually what happened when the current or when the voltage at the base is less than the threshold. Okay, so during the positive cycle, okay, these LC tank circuit will charging, and during the negative cycle of the input, okay, transistor will clip off the signal and this LC will discharge. Okay, so this LC tank circuit will operate, will resonate during the negative cycle of the output signal, and it will complement or it will fill out the missing half negative cycle. So we're gonna produce a full wave at the output. Okay. So LC tank circuit, remember LC tank circuit, it will only resonate during the negative cycle of the input, mixing input. Okay, during the negative cycle of the mixing input mixer, during the negative cycle of the mixing input, the LC tank circuit will resonate or discharge, which will produce the other half of the output signal. So during this process, okay, so this circuit will produce a complete, okay, double sideband full carrier waveform. Okay, so kalau kita lihat di sini uh, LC tank circuit ini dia akan charging, okay, dia akan charging during the positive cycle of the input. Okay, apabila input mixing daripada input ini melebihi threshold of the base at the base, maka outputnya akan menjadi dia akan mengalirkan output positif. Okay, apabila current ataupun voltage pada base itu rendah daripada threshold, maka transistor akan clip off the negative cycle of the signal, menjadikan kelihatan pada output itu cuma positive cycle sahaja. Tetapi disebabkan adanya LC tank circuit ini, ia akan resonate, ia akan melengkapkan gelombang tersebut dengan cara discharge the some amount of the voltage during the negative cycle, so that it will complement the whole process and it will produce the other half of the signal. So we're going to produce a complete set of double sideband full carrier. Okay. So the next part is the high level AM, high level amplitude modulation. So AM here is we want to produce a double sideband full carrier. Okay, so for high level, that means the output of the modulator uh, consume consume a high amount of power. Okay, the amount of power produced by the modulator is higher, and this signal is suitable for transmission. So we don't need to do extra amplification. Okay? So high level modulators can be classified into two categories. The first one is the collector modulator. The second one is the series modulator. Okay, so collector modulator. So this is the collector modulator. You see that carrier and input are separated into two different um, locations. So carrier is connected to the transistor over here, and here modulating signal. You see that modulating signal first will be amplified by the audio amplifier, and then it will be amplified again by the transformer over here. Okay, so this is the transformer. So the modulating signal over here consists of a high power modulating signal. So this is, you see that this is a VCC, so current will flow over here like this, and this is the LC tank circuit. So this is the LC tank circuit. Okay, so the current will flow towards here like this. Okay, so current can only flow towards ground over here if, okay, current can only flow to the ground like this only if the input voltage or the input current is more than the transistor threshold. Okay, otherwise the current cannot flow to the ground. Okay, so when the input voltage here at the base of the transistor more than the threshold limit, so the current can flow over here. Okay, so at this time the LC tank circuit will be charging. Okay, LC tank circuit will be charging. When the current or when the voltage at the base of the transistor less than the threshold of the transistor, the current cannot flow to the ground. At that point, LC tank circuit will discharge, it will resonate and produce the other half of the negative cycle of the AM signal. So this charging and discharge process, resonate and non-resonate process, will produce a complete output AM signal, positive and negative side. Okay. So here you see that here this is the amplifier use a class C amplifier. So amplifier has a class A, B, and C. Okay, so this is a type C of amplifier. And then a series modulator. Series modulator, we use two transistors. Okay, so each transistor is connected to the uh, modulating signal and also to the carrier signal. Okay, you see that here audio signal connected to emitter this transistor, and this carrier is connected to the another class C amplifier. Okay, so the current can only flow from VCC to the ground if the voltage or the current at the base more than the transistor threshold. Okay, otherwise the current cannot flow from VCC to the ground. Okay, so um, when the okay, so when the voltage at the base more than the transistor voltage, more than the threshold limit, at that time the LC tank circuit will be charging. Okay, so when the voltage at the threshold less than the when the voltage at when the voltage at the base less than the threshold, less than the transistor threshold, current cannot flow to the ground over here. Instead, it will uh, okay, it will this one the sorry, the current, okay, from sorry, yeah, if you see from here, if the voltage at the base more than the transistor threshold, what happen is that the current can flow from VCC to ground, and it will also charge the LC tank circuit. So when the voltage at the base is less than the transistor threshold, what happens is that the current cannot flow from VCC to the ground. Instead, at that point, the LC tank circuit will discharge and resonate to produce the missing half cycle of the negative cycle of the signal. So that's why during the at that time, this LC tank circuit will, during the negative cycle of the input, the LC tank circuit will resonate and discharge to produce the negative cycle of the output. Okay, so we're gonna produce a full set of positive and negative side uh, at the output. Okay, so so you see that uh, these both of these transistors, okay, is actually produce the contributes to the positive cycle at the output, where the LC tank circuit will contribute to the negative cycle of the output. Okay, but this process happens very quickly. Okay, this process happens very quickly, and we're gonna see. Uh, we didn't see the difference. We cannot see the changing is very fast, that we cannot see the difference. So from here we can see that the output is like a double sideband full carrier. We have the positive and negative sides. Circuitry of the double sideband suppressed carrier. Okay, so this is uh, how we want to generate the double sideband suppressed carrier signal. Okay, previously is how to produce the double sideband full carrier. Now, how can we produce a double sideband full carrier, a suppressed carrier? Remember double sideband suppressed carrier? Okay, double sideband suppressed carrier. Okay, so double sideband suppressed carrier only consists of lower sideband and also the upper sideband, and the carrier component has been suppressed completely. Okay, so double sideband suppressed carrier can be generated using the balance modulator, or what we call as the lattice modulator. Okay, so this balance modulator, okay, how does this balance modulator works? Okay, so first of all, we need to see that here is we have the modulating signal. Okay, modulating signal. Okay, so here we have two transformers, T1 transformer number 1 and also transformer number 2. Okay, over here at the ground here, below here we have the carrier. Okay, we have the carrier. So carrier has a higher frequency. Okay, so how does the circuit works? Okay, how does the circuits work? So during the positive cycle of the modulating signal, okay, during the positive cycle of the modulating signal, the carrier will undergo many changes from positive to negative. Because the carrier has a higher frequency, it will keep on rapidly change positive negative positive negative positive negative, okay, during the first half of the uh, input modulating signal. So if you see that at the beginning, for example, the polarity is positive and here is negative, for example. So the current will flow like this. Okay, so D1 will be closed circuit. D2, so you see that here the current will go like this also. Okay, so what happened is that D1 and D2 will be closed circuit and D3 will be open circuit. D4 and D3 and D4 will be open circuit. So the current flows like this. Okay, and it will be amplified at the output. Okay, so this is during the positive and negative. This is during the positive negative polarity like this. And then what happened when the carrier polarity change? Okay, what happened when the carrier polarity change? Okay, positive, negative like this. What happened? So the current will flow. Okay, the current will flow like this. Okay, so it will flow towards here, and it also will flow towards D3 and D4, but it cannot flow to the D1 and D2 because it will be reverse bias. So D1 and D2 will be open circuit. Okay, so the current flows, this one is supposed to be like this. So from D3 towards here, okay, and then from D4 towards here, okay, so and then it will be amplified, and then we gonna see a reverse bias. Okay, we're gonna see a reverse bias. So what happened is that so during this time the signal will be we'll see the negative cycle. So wait, I want to, maybe I need to draw, so maybe I can draw for this one. Okay, so if you see from here, okay, so this is the modulating signal, and then you're gonna see that uh, So the output will be like this. It will follow the shape. This okay. So during the positive cycle of the carrier, you're gonna see like this, okay, and then negative cycle of the carrier, then positive, negative, positive, negative, positive, negative. Okay, so at this point, the above here is D1 and D2 switch on. Below here is D3 and D4 will switch on. Okay, so actually maybe I need to draw over here. So actually here we have the over here we have the carrier. Okay, we have the carrier. The carrier oscillates faster than the modulating signal. Okay, so the changes happens. Okay, the difference happens. Sorry, you're gonna see the difference happens when the modulating signal change polarity from positive to negative. What happened? Okay, what happened? So you see that here, this one on. Okay, this at the negative side here when D3 and D4 switch on. Okay, so during the during the okay, maybe I will start from here. During the negative cycle of the carrier, because okay, maybe I'm gonna show from here. This one supposed to be go down and then go up. Okay, so maybe I delete for a while this one. So in the drawing actually needs to be synchronized. Okay, so I maybe I draw like this. Okay, so you see that what happened is that the carrier signal goes to the negative cycle, but at that time the modulating signal changing polarity from positive to negative. Okay, so what happened is that when the during the negative cycle of the carrier, okay, during the negative cycle of the carrier, the output will produce positive. Okay, during the positive cycle of the carrier will produce negative, and during the positive cycle will produce this one during the negative cycle will produce the positive. Okay, so this is inversion. Okay, terbalik. Okay, 180-degree shift. Okay, so during the positive cycle it will produce a negative output. During the negative cycle it will produce positive output, and so on. Okay, so you see that uh, uh, these the output uh, the output produce the output is invert. Okay, from the previous wave, from the previous initially during the positive cycle of the modulating signal, the output follows the polarity of the carrier. However, during the negative cycle of the modulating signal, of the input signal, the output is reverse polarity from the carrier. Okay, so over here is what we call as a 180-degree phase shift. Okay, where after this the output is invert. Okay, invert from the is the reverse from the carrier polarity. If the carrier is positive, the output will be negative. if the carrier is positive, the output is negative. If the carrier is negative, the output is uh, if the carrier is positive, the output will be negative. Okay, and if the carrier is positive, the output will be positive. So it will be invert. Okay, reverse. So this is the process that happens inside the balance modulator. Okay, and mathematically this is a multiplication process actually. Yeah? Okay, mathematically this is the process of multiplications. Okay, so so the output is actually VAM SC. Okay, function of time. So this is actually VCT multiplied with VM. Okay, so if I do this, this is a VC sine 2 pi FCT multiplied with VM sine 2 pi FMT. Okay, so what happened is that we will produce a VCVM sine 2 pi FCT sine 2 pi FMT. Okay, and this is actually VCVM over 2. So sine and sine will produce cos. So this is cos 2 pi Fc minus Fm, the lower sideband, minus cos 2 pi Fc plus Fm. So this is the upper sideband. Okay. So when we draw the spectrum, frequency spectrum, okay, when we draw the frequency spectrum, what happens is that like this. Okay, so this is the carrier component. There's no carrier component. Carrier has been suppressed. Here is Fc plus Fm. Here is Fc minus Fm. And the amplitude over here is VCVM over 2. Okay, VCVM over 2. Okay, it's not VM over 2. Okay, so students normally do careless mistakes. They assume that the output is VM over 2 for the double sideband suppressed carrier, which is not true actually. So remember, when you want to draw the frequency spectrum, first of all, you need to do the equations. Find the equation first. Okay. From here, you can see how much is the amplitude, how much is the frequencies. Okay. So we have seen how the method to produce to generate double sideband full carrier. We also have seen the method to produce double sideband suppressed carrier using balance modulator. And then we will see how can we will see the process of generating SSB. Okay, how to generate SSB signal. Okay, so we have two methods over here. Either we want to use a filter method or we want to use a phasing method. Okay, so filter methods means that we use filter to remove the unwanted frequency component. Okay, so you see from here filter method. Okay, so first of all, we generate double sideband suppressed carrier. Okay, using a balance modulator, we're gonna produce a DSB-SC suppressed carrier. Okay, so this is the carrier. This is a VCT. Okay, this is the VMT. Okay, so here we produce a double sideband suppressed carrier. So we have two sidebands without the carrier component, and then we use filter to choose the sideband that we want and to remove the unwanted sideband. So in this example, it will select the upper sideband and uh, it will remove the lower sideband. Okay, so it depends. You can also choose the lower sideband and remove the upper sideband. So either you want to use a low pass filter or you want to use a high pass filter. Okay, so the output here is a single sideband, and then we amplify the signal and then we transmit. Okay, we transmit the single sideband. And then single sideband generation using a phasing method also. Okay, so this is using different kind of filters. Okay, we have the upper sideband filter and also the lower sideband filter. This is actually quite similar with this one, quite similar. So this one, picture A, is quite similar with the is actually similar with the previous picture where we have the VMT, we have the VCT, okay, and then go to the it goes to the balance modulator. So balance modulator will produce double sideband suppressed carrier, and then we can choose using a filter which is a upper sideband filter and lower sideband filter. So this is a low pass filter. Okay, this is a low pass filter and this is a high pass filter, HPF. So we can choose which sideband we want to produce. Okay, we want to maintain, and then goes to the frequency translator, and then amplify the signal, and then transmit. Okay, and then here, if you see from here, the picture B over here, VMT over here, VMT input, and then this picture in picture B, it used two sets of carrier. Okay, carrier 1 and also carrier 2. Okay, so this carrier has different frequencies. So and then we have here one type of filter only. So this actually will produce double sideband suppressed carrier. Okay, but the frequency would be different. Okay, so the filter gonna choose which sideband that we want. Okay, so this is either low pass filter or high pass filter, and then the signal goes to the frequency translator and then amplified and then transmit. Okay, so this is based on the filter method. Okay, filtering method. So we can also produce single sideband without using filter. Okay, without using the filter. So this is a phasing method. So the phasing method will remove the unwanted sideband based on the different phase. Sorry, based on the by filtering based on the phase. Okay, we, uh, we filter out based on different phase. So in mathematically, it can be cancelled out. Okay, so how does the system works? Okay, so I will show you, because this picture or this example has been come out in the previous semester's final exam. Okay, where the student was asked to derive the equations, okay, from at a few point, from this point, and also at the output. Okay, so maybe I need to redraw again so that you can have more understanding about it. So I will draw over here. Okay, I will draw over here. So if you see that here we have the modulating signal, and here it goes to the first balance modulator. Okay, and then here we have a 90-degree phase shifter. Okay, 90-degree phase shifter, and then this goes to the second balance modulator. So I put here as a BS, a balance, BM, balance modulator 1. This is a balance modulator 2, BM2. Okay, BM2. Okay, so this is a VMT. Okay, and over here we have the VCT. Okay, over here we have the VCT, the carrier component. The carrier signal will go to the first balance modulator, and then over here we have the 90-degree phase shifter, PS. Okay, phase shifter, and this goes to the second balance modulator. Okay, so the output here will goes to the adder. We have adder over here, and then it goes to the output. Okay, so what happened is that assuming that VMT is equal to VM sine 2 pi FMT, while the VCT is equal to VC sine 2 pi FCT. Okay, so what happened? So at this point, okay, at the first balance modulator, okay, at the first balance modulator, you see that it goes like this. Okay, so the output like this. Okay, so what happened at the first balance modulator, BM1? What happened over here? Okay, so over here you see that this is X, or this will do the process of multiplications. That means VMT will be multiplied to the carrier signal. So here the output here is actually VC VM sine 2 pi FCT. Okay, 2 pi FCT sine 2 pi FMT. Okay, so this is actually will produce a double sideband suppressed carrier, which is VC VM over 2 in bracket cos 2 pi, and this is a lower sideband FC minus FM. Okay, T minus cos 2 pi FC plus FM for the upper sideband. Okay, so this is at the first balance modulator. Okay, ini yang berlaku pada balance modulator yang pertama. What happened at the second balance modulator? So you see that this is a 90-degree phase shift. So 90-degree shift from the sine function, you will produce a cos function. Okay, cosine function. 90 degree of sine is cosine. So here is Vm cos 2 pi FMT. Okay, and here carrier also will be shifted 90 degree. So over here is Vc cos. Okay, sine become cos. So 90 degree phase shift for the sine function will produce cosine function cos 2 pi FCT. Okay, so what happened at the output? Okay, what happened at the output of second balance modulator? Okay, Again, both of these will be multiplied. Okay, VCT will be multiplied with the VMT. Okay, so this is will produce same like this, VCVM, VCVM, but now is cos. Okay, cos 2 pi FCT cos 2 pi FMT. So cos and cos, according to trigonometry identity, will produce cos and cos, cos plus cos. Okay, so actually will be like this: VC VM over 2, okay, cos 2 pi FC minus FM for the lower sideband, okay, and then here is, you see that here is plus, okay, plus cos 2 pi FC plus FM T, close bracket. So what happened is that, you see, so output from BM1 and output from balance modulator 2 goes to the adder, okay, adder over here. So adder will do the process of summation, okay. So this the above part will add to the lower part. Okay, so when we do the summation process, what happened during the summation process? These component can be cancelled out because this is minus and plus, so we can cancel out the upper sideband. Okay, we can cancel out the upper sideband. Okay, because this is plus and minus, so it will be cancelled out. Okay, and 1 over 2 VCVM, okay, half VCVM plus another half VCVM. So we're gonna produce VCVM at the output. Okay, so the output here is that we plus this cos and also this cos. So therefore the output here is VCVM cos 2 pi uh, FC minus FMT. So in this case, in this example, it will produce a lower sideband. Okay, it will produce a lower sideband. Okay, so this is the output is actually a single sideband without carrier. Okay, so if we draw the frequency spectrum, okay, if we draw the frequency spectrum for this one, okay, so here is the, for example, here is the FC over here. So this is FC minus FM over here. Okay, FC plus FM is here, but there's no upper sideband. Okay, there's no upper sideband. Okay, this is F. Okay, so this is a frequency axis. Okay, the axis here is F frequency, and here we have okay, the amplitude is VCVM. Okay, there's no carrier component. Okay, no carrier component, no upper sideband. Okay, so and then if we look from here, oh, it has another amplifier. Okay, for example, here if I continue, if I continue this output, okay, if I continue, for example, here we have maybe I draw here, maybe we have for example here we have another okay, okay, so for example here X, okay, output here is X, and then goes to the amplifier. Okay, I redraw again over here. For example, the output goes to the amplifier. Here, remember X is the SSB without carrier, WC. Okay, and then for example here we have an amplifier with a gain of for example 10 dB for example. Okay, what happened? So 10 dB is equal to 10. If you do anti-log, it will produce 10. So the output here is supposed to be 10x. So what is 10x? Okay, so 10x means that means the output here 10 times of VCVM. Okay, so that means the output here after, let's say if we have the amplitude, the amplifier over here, let's say we have the amplifier with a gain of 10, so therefore the output gonna be 10 VCVM. Okay, 10 VCVM cos 2 pi FC minus FM T. Okay, and if you draw the frequency spectrum after the amplifier, for example we have the amplifier, so after amplifier, um, so this is for example voltage versus frequency. So the output here is, for example, here is FC and here is FC plus FM, here is FC minus FM. Okay, over here, so that means we have the output over here, the amplitude is 10 VC VM. Okay. So this is many in this up to here actually many students were doing many students did careless mistakes at this point. Okay, because they assume that the output is VM over 2, which is wrong actually. For the single sideband, when we want to draw the frequency spectrum, it must be based on the equations. Okay, it must be based on the equations. Okay. So from the previous exam questions, the exam question asks up to here also, where the question asks draw the frequency spectrum, draw the amplitude spectrum. So the amplitude spectrum only consists of lower sideband, and the amplitude is uh, like this. For example, here is 10 VCVM, for example. Okay, because I use a 10 dB of the amplifier. So it depends if different value of amplifier, that means the output gonna be different than 10. Okay, so here is 10, so that means I use 10 for the amplifier, so the output is 10 times VCVM. Okay, so from here actually you can calculate the total power. Okay, power is equal to PLSB only, because there's no carrier, there's no upper sideband component. Okay, so what happened is that here is uh, here is 10 10 VCVM. That means this is the power is 10 VCVM square divide with 2R. Okay, so you will get the value here is x in terms of what, in terms of what. Okay, and the previous final exam also asked up to the power calculations. Okay, previously students did a careless mistake also. What they do is that P total is equal to PC in bracket 1 plus m square over 2, which is wrong. Okay, so when you want to find the total power, first of all you need to know how many how many components at the output. Okay, how many components at the output. So since this example only for the single sideband, so we only have one component only. Okay, we only have one component, which is the lower sideband. Okay. Okay, so this is how we produce the output. Okay. Again, in the previous final exam, also we have the amplifier. Okay, at the output of the single sideband modulator. Okay, so with a certain value of a decibel, so that means the output needs to be multiplied with the gain. Okay, so here the gain, uh, 10 here is the gain, A, okay, which is this one. Okay. Okay, so now you know how to uh, write the equations. So you see that we don't use the filter. Okay, we use a phasing method. We use a different kind of phasing, a different phase to eliminate, to remove the unwanted sideband. Okay, based on the design of the system. Okay, so you know how to write the final equations. You know how to draw the amplitude spectrum. You know how to calculate the total power. Uh, okay. So I go back to the slides. Okay, I go back to the slides. So in this example, it will produce. This example will produce a single sideband without carrier, SSB without carrier. But in this example, it will produce a lower sideband. Okay, lower sideband in this case. We can also produce upper sideband by changing this arrangement of blocks. Okay, we can produce the upper sideband. Okay. So the method is based on simple fact that two signals that differ in phase by 180-degree opposite or flip over will cancel each other and produce zero results when they are added together. Okay, so this is the phasing method. So this okay, this already been explained. Okay, so now is about diode. This is about a demodulator at the receiver. Previously, we have learned about the modulator, which is inside the transmitter. Now, for the demodulation process, happens at the demodulator, which is in the receiver. Okay, so there are many types of demodulator. Okay, many types of demodulator, but in your syllabus, we only show two types of demodulator, which is diode detector and also transistor detector. Okay, so the word detector here means demodulator. Okay, and AM here is for the double sideband full carrier. Okay, so this is the simplest demodulator circuit, which is diode demodulator. So over here we have at the left side, okay, at the left side we have the AM signal. So AM signal goes from left to the right. Okay, so this is a double sideband full carrier, DSB-FC. Okay, and then we have the first diode. Remember, diode only allows current to flow in one direction only, and it will cut off the reverse bias. It will prevent the reverse bias. So there's no reverse bias. Okay, there's no reverse bias. So during the forward bias, the RC tank circuit will charging. Okay, RC tank circuit will be charging. this RC will resonate at the carrier frequency. Okay, this RC will resonate at the carrier frequency during the negative cycle of the output. Okay, RC is the function of RC here is like the LC tank circuit previously in the modulator circuit. Okay, so and then here we have another capacitor. Okay, so the capacitor discharge only slightly when the diode is not conducting. The resulting waveform across the capacitor is close approximation to the original modulating. Because the diode detector recovers the envelope of the AM signal, the circuit sometimes called envelope detector. So if the RC time constant in the diode detector is too long, the capacitor will discharge uh, will be too slow to follow the faster changes of the modulating signal. This is referred to as diagonal distortion. So the RC, the value of the RC needs to be suitable so that the process of charging and discharging follows the changes of the waveform. Okay. Okay. So I will show you that here. Maybe I will draw like this. So you see that the signal is actually like this, and the signal is actually like this. Okay, and actually the signal initially like this, the AM signal, it consists of the uh, double sideband full carrier signal. Okay, it has the negative cycle at the beginning. Okay, it has the negative cycle at the beginning. Okay, so this is actually follows. Maybe I redraw again. Sorry. So this is the double sideband full carrier waveform at the input of the demodulator. Okay, at the input of the demodulator, this is uh, the input signal. Okay? The input over here, double sideband uh, full carrier. And then what happened? It goes through the D1. Okay, so diode, the function of diode is like a switch where it only allows current to flow in one direction only. So during the positive cycle, it will switch on. During the negative cycle of the input, it will switch off, which is during the reverse bias. Okay, so what happened? When the signal passed through the diode, okay, when the signal passed through the diode, what happened is that the negative cycle will be clipped off, okay, will be removed. Okay, so the output of the diode will be half of it. Okay, half of the DSB-FC waveform. Okay, separuh daripada double segment full carrier. Okay, and then uh, okay, so half of it. So remember that during the positive cycle of the signal, which is this one, during the positive cycle, RC tank circuit will be uh, charging, and during the negative cycle, RC tank circuit will be discharged. Okay, So due the RC tank circuit, what happened is that it will prevent the signal from going down like this and from moving down towards the negative cycle. Instead, it will slowly varying the output. Okay, it will slowly varying the output. Okay, so during when the this is when the RC tank circuit discharge, and then positive cycle RC tank circuit will be charging again, and then it will discharge by slowly varying like this. It will slowly prevent the signal from going down. Okay, and then charging, discharge, charging, discharge, charging, discharge until the end. Okay, so you will see that the signal is actually like this. Maybe I can redraw again. Okay. So it will be like this. So the shape here follows a sine wave. Okay, you see that the shape here follows a sine wave, but it is not smooth. Okay, it is looks like a sawtooth like this. Okay, dia tidak smooth disebabkan because due to the charging and discharging process, the output signal is not smooth. Okay, it's not a smooth. It's not a smooth sine wave. Okay, because of the charging discharge of the RC tank circuit, the output looks like a sawtooth sine wave. Okay, dia terlihat seperti bentuk gergaji sine wave. Okay, but this is after, if you see that this is after the RC tank circuit, the signal looks like the sawtooth like. Okay, sawtooth like. Okay, so uh, so this is the output after the RC tank circuit. Okay, we have the sine wave. We have a waveform look like a sine wave, but it's not smooth. It's like a sawtooth sine wave. Okay, so this is the output after the RC tank circuit. Okay, and after the RC tank circuit, we have another capacitor. Okay, if you see that we have another capacitor, what is a C2. So what happened after the capacitor, after the C2 capacitor? How does the waveform look like? So capacitor C2 will remove DC component. Okay, it will remove a DC component. So what happened? So you see that the signal is above here. Okay, the signal uh, is the signal has a DC component. Okay, the signal has a DC component over here, so that you see that the signal is located above the x-axis. Okay, so capacitor C2 will remove this DC component. Okay, it will remove this DC component. So what happened is that this signal will go down to the x-axis. Okay, so the x-axis now, okay, okay, so the signal will go down to the x-axis. So I redraw again the axis. So the x-axis will be over here. Okay, the x-axis will be over here. So capacitor C2 will remove the DC component, remove the DC voltage, and the signal will be starting from the will be go down at the zero axis, at the x axis. Okay, pada paksi x. Okay, the signal will go down to the x-axis. So it will start at the 0 volt. Okay, the signal will start at the 0 volt. Previously, the signal starts at DC voltage. Okay, so now the signal starts at 0 voltage because of the C2 capacitor will remove the DC voltage. So the signal goes down to the x-axis. Okay, so actually the signal will be like this. This is like this, for example. Okay, but it is not smooth. Okay, it is not smooth. Okay, so this is the output of the diode demodulator. Okay, so how to make the output signal smooth sine wave? How to make a smooth sine wave? So we need to use a set of filters. Okay, to smooth up, to make the output signal smooth, smooth sine wave. Okay, so that means we need a additional filter. Okay, to make the output signal smooth, smooth sine wave. Okay, so this is, what is this actually? This is the VMT. Okay, so demodulator to convert double sideband full carrier to become VMT. Okay, remember demodulation is the process or is the reverse process of modulation. Okay, we want to get the original input signal VMT. Okay, we want to get the original VMT. So this is actually to produce a VMT. Okay, the modulating signal. Okay. Okay. So therefore, we get the output of this demodulator circuit. We produce a sine wave VMT, but it is not smooth due to the charging and discharge of the RC tank circuit. Okay. And we also have another type of transistor detector. Okay, another type of demodulator, what we call as a transistor detector. Here is a transistor, and this is the AM signal at the input. This is a double sideband full carrier. Okay, and we have here RC tank circuit. So the process is quite similar with the diode detector. Okay, so this transistor will remove the negative cycle of the double sideband full carrier. Okay, and then during the positive cycle of the double sideband full carrier, RC tank circuit will charging. Okay, so during the during the negative cycle of the double sideband full carrier, negative cycle of the input, RC tank circuit will resonate and discharge. So what happens is that it will fill out the negative cycle. So therefore, we're gonna get a complete positive and negative cycle. Capacitor C3 will remove the DC voltage. It will remove the DC component so that the signal will go down to the x-axis again and starts at 0. Okay, so the signal initially from above here. Okay, and now it will go down to the x-axis. It will start at 0 voltage, like a sine wave, like this. Okay, so capacitor C3 will remove the DC component, and therefore the output signal will go down to the x-axis and starts at 0. Okay, starts at 0 like this. Okay, so the output here is actually not smooth because of the charging and discharge of the RC tank circuit. So we need additional filters to smoothen the output signal. Okay, see that C3 remove the DC component. Okay, The next topic is about double sideband, the, the detector for double sideband, suppressed carrier, and also for the single sideband. Okay, so this is actually referring to the double sideband suppressed carrier and also for the single sideband. So how we want to demodulate the double sideband suppressed carrier and also the single sideband. Okay. So for example here, we need to use a balance modulator at the receiver. Okay. We need to use a balance modulator at the receiver in order to produce the original output VMT. Okay. So you see that here is the input signal, for example, here is the SSB without carrier. Here is the upper sideband FC plus FM. And then here we have a balance modulator. So you see that this is the demodulator part. Okay, this is the demodulator process. Okay, the process inside the demodulator. Okay, we also have the balance modulator inside the demodulator. Okay, so we need to introduce a balance modulator. Okay, so here is the oscillator which oscillate at the carrier frequency. Okay, so balance modulator will do the process of multiplication. Okay, so FC, so the input multiplied with the carrier or with the oscillator frequency signal. So what happens is that it will produce upper and lower component. Okay, upper component is plus, lower component is minus. So this is the upper component, this is the lower component. Okay, so FC plus FM plus FLO or FC plus FM minus FLO. So this is a USB, this is the LSB. Okay, so when you plus all of this, you're gonna get 2FC plus FM for the upper side frequency, and for the lower side frequency, you're gonna get FM. And then we need filter to filter out the unwanted frequencies. So we use low pass filter to remove the upper side frequency and take the modulating signal frequency FM. So therefore we get output FM over here. Okay. The next topic is about receiver parameters. Okay. Receiver consists of many parameters, but here we will focus on certain parameters only for the receiver. The main parameters for the receiver. Okay. So the first one is about selectivity. Okay, if you see that this is for the filters parameter in the receiver. Okay, selectivity. Selectivity is the ability of the receiver to accept a given band frequency and reject the others. So the receiver must have a very good selectivity uh, characteristic. Okay, where it can select a certain bandwidth and reject the other unwanted bandwidth frequencies. Okay, so this is actually the filter parameters actually. The filter parameters at the receiver. Again, that means the filter at the receiver side must be good enough to select a certain frequencies and reject the others. Okay, so how to measure the selectivity characteristic? Okay, we can use what we call as a shift factor. So shift factor, this is a filter shift factor, is equal to the bandwidth of minus 60 dB divided with the bandwidth of minus 3 dB. This is based on the frequency response curve. Here, this one. So I skip to this graph. We see that this is the frequency response of the filter inside the tune circuit in the receiver. Okay, so this is the frequency response curve. So we see that minus 3 dB is over here. So that means the bandwidth of 3 dB is from here to here. Okay, and minus 60 dB is somewhere here. Okay, minus 60 dB. Okay, so this is the minus 60 dB bandwidth. Okay, so um, theoretically, we want a filter to have a very sharp cutoff. We want the best filter would be to have a very sharp cutoff like this. Okay, which is not happens in the real world. So theoretically, we want the filter to be as sharp as possible, to have a very sharp cutoff. Okay, that's we don't want this skirt like this. Theoretically, okay, theoretically we don't want these sides. Okay, we want to select this one. Okay, in the middle here. Okay, but in practical, in the real world, of course, the filter response looks like this. It have a curve like this. Okay, in the real world, in the practical case, the filter will have frequency response like a bell curve like this. Okay, only based on the best filter will be as sharp as possible. Okay, the filter can be as sharp cut off as possible. So this is based on the filter design. Okay, the nearest to the 3 dB cut off will be better. Okay, so this is as I say that we want the filter to have a very sharp cut off of the frequency response. Okay, so sometimes the signal can be like this, like this, like this. Okay, so the sharper the filter, the better would be. Okay, so if the selectivity factor is so this is actually less than uh, okay, so this is actually we want the bandwidth here to be similar with bandwidth of minus 3 dB. Okay, so if selectivity factor is equal to 1, which is the ideal case, it will be much better. Okay, so we can remove all the unwanted frequencies component. Okay, so if you see from here, the bandwidth of minus 60 dB is larger than the bandwidth of minus 3 dB. So here you're going to get the value more than 1. Okay, the value going to be more than 1. However, we want the shift factor to be close as possible to the value of 1. Okay, so that it has a very sharp cutoff. So selectivity also has another parameter, what we call as the Q factor, quality factor. So quality factor is equal to Q, which is inductance reactance divide with the resistive. Okay, and we can also measure the bandwidth of the tune circuit. Of the tune circuit. So tune circuit is the first part of the receiver, the part that the block that receive the signal and filter out the unwanted frequencies. Okay, so this is the bandwidth of the tune circuit, the first part of the receiver. Okay, that consists of filters. So bandwidth of the tune circuit is equal to the resonant frequency divided with the quality factor. Of course, bandwidth has the unit of hertz. Okay, Q has no unit. It's a unitless parameter because this is ohm divide with ohm. Okay, impedance divide with impedance. So this is no unit parameters. Okay, and then the second parameter is the sensitivity. Okay, so sensitivity define the minimum RF signal that can be detected. Okay, if your receiver can detect a very small amount of signal, that a very small amplitude of signal, that means your receiver is very sensitive. Okay, because the signal when travel from transmitter to the receiver, the signal will attenuate. Okay, signal will attenuate from transmitter to the receiver. So the signal, when it arrives at the receiver, the amplitude will be much, much, much smaller. So the receiver must have the ability to sense the signal and receive the signal and demodulate the signal. Okay, not only we can receive the signal, the receiver must be able to receive and demodulate the signal. Okay, so that's the ability. That one is under the category of sensitivity. So the more sensitive the receiver, the better would be the output signal. Okay, so bandwidth improvement factor, this is also for the tune circuit. Bandwidth improvement factor is bandwidth of the RF radio frequency divided with the bandwidth of the intermediate frequency. Okay, what is that? We're gonna see later about intermediate frequency IF. So you see that initially we have a FM, okay, and then when we do the modulation process, okay, we produce a double sideband full carrier at the higher frequency, and then during the demodulation process, what happened is that we are not translating the frequency to FM directly, but instead we translate the frequency into intermediate frequency. Okay, so this is a IF over here. This is a RF. Okay, so when we do the demodulation process, first we downgrade. Okay, we down convert the frequency from RF to intermediate frequency. So RF, what is RF? RF is the AM frequency. Okay, into intermediate frequency is around 455 kilohertz, something like that. Okay, so after IF, we down convert into the original modulating signal frequency. Okay, so the bandwidth of RF, this is the bandwidth of RF, and this is the bandwidth of IF. Okay, so this one has no unit, and then when you do the decibel value 10 log of BI, so this is in term of dB. Okay, so the lower the value would be better. Okay, so that's all for now. I will explain later about example 2.11. Okay, I will explain later about example 2.11. So that's all for now. Bye bye.